Good morning, everyone, and welcome to this third edition of the BATT4EU Success Stories, a webinar powered by BEPA, where we go through the results and the achievements of the different projects which were funded under Horizon Europe and under the BATT4EU partnership. So today we will be having first Alexander Thaler from the Batwoman project, from the Giga Green Green Speed project. Oh God, I'm sorry, from the Green Speed project. And afterwards we'll have Marcus Jan from the Batwoman project. And lastly, we'll have Stina Starborg from the Nova project. Just a few housekeeping rules as we start. The meeting is recorded, and after the webinar is finished, we will be sending the slides and the recording to the audience via email. Please don't hesitate to ask questions during the presentations. There will be a bit of time for Q&A after each presentation, where the speakers will be able to answer to you. You can post them in the chat and in the Q&A section. For any technical issues, please don't hesitate to also leave a message in the chat. And please keep your microphone and camera deactivated while someone else is presenting and speaking. And of course, stay updated for the future editions of this webinar, because there will be many more, as there are many projects that are funded under the BATT4EU partnership and which we will be sharing the achievements of. Without further ado, I will leave the floor to Alexander Thaler for the Green Speed project. Alexander, please, the floor is yours.
Yeah, thank you very much from my side and from the Green Speed project. I hope you can see the screen. At least I'm sharing.
Yes, we do.
Yeah, I will be first out of 3 projects coming from the same core, so it will be fitting together what you see. And my job now is, as a technical leader of the Green Speed Consortium, to introduce you to our project. What waits for you? So first of all, I would like to give a short introduction in what was back then. It's almost 4 years gone. What was back then the high-level challenges from this call and where these projects are focused on. And of course, I will give you an introduction into the Green Speed Consortium. Then we go with a technology overview for the project, and I will also try to explain what will be the focus of the meeting today and of the discussion today. Yeah, and then we go for some technological deep dive. I'm an electrical engineer, for your information, so that might be also important. I won't give you very much information about electrochemical details, but hopefully to the ones of you who are interested in a more high-flying insight on the project, that will be my job to do. And then we go for the anode, the cathode, and see what at the end ends up at the full cell and some results. And then there will be a summary on the project and the project demo, what we learned, at least also from my side. And very important also to mention, at the very beginning, there will be a link to a webinar out of the Green Speed project, which will be held on mid of December. You can find that information later on. We would be happy to have you joining, because there we go much more in depth, and there you also have the expert to ask questions towards. So now let's start for the high-level topics and following the technological overview of the project. So back then, and it's still now, we have these high-level challenges in Europe to have a European battery industry, even more than 4 years ago. Then we have the high energy consumption of single production steps, low energy density on the cells, and a higher demand of EVs, as you remember, and the use of environmental harmful substances used in the production that needs to be reduced. And of course, cost is a big issue. So now for today, I would like to focus on the very left topic, which is what processes can be used and applied to get down the energy consumption of single process production steps, and on the other side, of course, the same way, reduce the environmentally harmful substances of that. The consortium, we are very Central Europe heavy, not intentionally. It actually was probably accidentally developing out of the project 5EP, where some of the partners were already participating. And as you also can see, we are, as a project, we are quite industry heavy. I would just start with the western part, which is Arkema, French company, you know that, dealing in our project with specialized binders and electrolyte topics. On the bottom, you see circuit foil, quite specific topic when it comes to anode current collectors, optimization of that. We have a very innovative partner in our consortium, which is Leidenschar. You probably already know about their pure silicon anode, which we also try to utilize, and we did that. And on the German side, BMW as a lead for the final product, the EV, Forschungszentrum Jülich, dealing with anode topics, pre-lithiation. Umicore is a partner for active materials on the cathode side. Spira is another partner, which is again dealing with the current collectors. ZSW on the cathode side, and there is the Austrian part of it, AVL system integration, Varta cell integration, and us somewhere in the middle, doing some support activities on the virtual upscaling and integration of the technology. Now, what is done as a big overview? I tried to just depict the process chain of how a cell is getting manufactured, and you have on the very top left, you have the things we do on the cathode side. So it is the focus on a nickel-rich cathode that is going for a solvent-free process. We do on both sides, anode and cathode, optimize the current collectors, and we have also a task in which is dealing with AI and getting an idea how these processes can be optimized faster than just trying. So there was also some interesting results on that. On the lower end, you see the anode part. There is one branch dealing with close to market materials. That means a mix of graphite and silicon to a high extent, so bigger than 60%. And we have, as already mentioned, Leidenschar with the pure silicon anode. That is dry processed, very new, very innovative technology. On the anode side, further pre-lithiation, and now I just get rid of the rest, what we don't want to talk today, because it would be just not fitting into the 15 minutes. That is what we will have on the cathode side, the anode side, and of course the outlook at the end towards the project results. The project is in its final stage, so it will end this year. So there are some results pending, but we are quite in a good shape when it comes to demonstrating our results. So first step towards anode. You see here 3 main tasks. One is the anode formulation, and again you see the two branches on the anode side, which is the silicon graphite composite produced from a wet process, and we have the innovative part, pure silicon with this Leidenschar process. And you see here the partners who are contributing to that. Of course, there's always Arkema with the binder topics within, and BMW supervising the process. And Varta really wants to understand, they are doing actually the silicon graphite content, and of course are very interested in understanding how this then can be further integrated into the full cell. As mentioned before, the anode substrate, the copper foil is one part of it, because when you think about putting pure silicon on a current collector, you know that there will be a lot of mechanical stress. Circuit foil was having a nice solution on that. They deal with the modification of the anode substrate, to that sense that these high silicon anodes can be attached to that quite well on the adhesion side, but also improving the lifetime on that. And to get all these high energy dense materials work, there is one big part dealing with pre-lithiations, which is Forschungszentrum Jülich, actually on both of our anode solutions. So going now for the first result, we have on the left side, you see the graphite silicon part, as I said, in combination with the NMC 811. And you see how these single optimization steps are dealing with towards the cycle life. So we have the improved capacity of the anode, which is the one. Then we have the electrolyte, and then we have the copper substrate, and we end up, somewhere around this 200 cycles within this SOH 80% remaining. And on the right side, of course, much higher challenging, pure silicon, dry processed also towards NMC 811. Here we have these two improvement steps combined. So you see there is a lot of things that can be improved. And both of that are roll-produced processes. So that's a little bit the thing also we have within the consortium, that we try to really go for the machines that allow for later upscaling. A special topic for the pre-lithiation, also that was done on the Jülich production line, or Jülich pre-lithiation line, on the roll-to-roll basis. And you can see on the right side, without and with pre-lithiation, an increase of 30% of the cycle life. So the excess lithium is there, and it's showing its result in the final cell. On the pure silicon, there were some investigations done when it comes to degree of pre-lithiation, and you see here the reference in red, one pre-lithiation step with 5% on green, and the 10% in blue. And you see the different behavior on the area capacity towards the final cell, and on the other side, the Coulombic efficiency, how that differently behaves through that development. What might be important to say, that the pure silicon anode was not processed on the roll-to-roll. It was actually done with a bath pre-lithiation, but the results are obvious that things are important to investigate towards the pre-lithiation degree, and how that is then behaving to the final cell. Okay, cathode part. Of course, material development needs to be done. Binders, current collectors, Arkema, Spira, and Umicore are here partnering. And then ZSW do the dry coating, and some part is done here with the artificial intelligence to optimize and get an idea where this process can be optimized in a simple way. Dry processing, a very brief overview on the left. The dry power is mixed, hopefully homogeneously mixed. Then it's done, then it's transferred to the extrusion and roll-to-roll transfer. We have ethylene carbonate in as a processing additive that needs to be removed now after the extrusion process, and then calendering is done. And if you want to look in a more detail towards the structure of this process, you have here these chamber where you put in the dry active material. Then this is going for the extruder. Throughout that extruder, this active mass is formed, and then it's going through the slot die and is transferred onto the current collector. Later on, so that brings down the energy demand because the process steps are very much condensed to what is really needed. So what was the main challenges? And hopefully that picture you see on the right is not the final one. Searching for uniform films. The shapes of the edges is a critical thing. The adhesion until now is a big challenge. And of course, mechanical stability towards bending of the foils is a thing. And due to the scene that this process is one-sided, coating on the current collector, it's a challenge to match the desired loading for the both sides. So all the process steps were optimized. We have some electrochemical performance, and there is also a stable process now enabled with double-side coating. And the digital twin showed also some reasonable results to optimize the process itself. To the cell. Electrolyte, when it comes to lifetime, it's a very important topic. We have Arkema here as one of the key partners. These electrolytes are optimized towards different anodes and look at the cathode. Then the big thing of Varta is the cell integration into one pouch cell and the 21700 cell format. And of course, there is testing and validation due to the fact that we have set up quite neat requirements. We try to fit to them. Again, these two parts of the results. In green, the anode silicon graphite cell as a multi-layer pouch cell, and the black part is the pure silicon anode. You see there a decrease in direct current resistance for the anode. For the pure silicon anode. And on the right side, you see the results from the cylindrical cell, 21700 manufactured by BATT, different C rates, and probably there might be some optimization for really doing a product out of it, but the experts say that this is already quite a good result towards carrying this type of cell and electrode towards the 21700 further. Finalizing the results, you see a huge drop in internal resistance when it comes to the pure silicon anode. And it seems to be that with this technology, we might meet the DCIR requirements, at least to some extent. And you see the references we were putting to ourselves on the high energy side, on the high power side, and a little bit as a result spreading over the state of charge of the single cell. Summary of the project demo. So we hardly tried to get to all these innovative processes towards demonstrated in full cell. So that is the high silicon content anodes, both in stacked pouch cell or one-top cell, and the dry process cathode is also demonstrated in pouch cells. So the NMP is not there in our process anymore. We gathered a lot of data regarding the process chain, especially when it comes to energy and cost, and of course the interfaces between the partners and the processes. And the energy demand and the cost are assessed, and we have this modeling activities supported. And we learned a lot about interfaces when it comes to shipping of this kind of precious parts between the partners. It might be one of our challenges in Europe that we spread our work between different partners, and that is also brings up the necessity to take care for these interfaces. Now I'm finalizing my talk. It's that information if you want to go in depth towards the webinar. And I want to thank you for your attention.
Thank you very much, Alex. Thank you so much. Great presentation. Thank you. I don't see any questions as of yet. And in any case, I think it might be time that I move on to the next guest to keep the time. If you have any questions for Alexander Teller, please don't hesitate to put them in chat and Q&A. And Alex, you may answer in writing directly in
Yes,
that
of course.
case.
Thank you.
Thank you so much. I will now move on to our next speaker, Markus Jan, who will today be presenting the results and achievements of the BATT4EU project. Markus Jan, please, the floor is yours.
Hello, good morning, everyone. Hope you can hear me okay and see my screen okay.
Yeah, perfect.
Wonderful. So yeah, thank you very much for having me, for having the BATT4EU project for this workshop. My name is Markus Jan. I'm working at the AIT, Austrian Institute of Technology, which was the coordinator for this project. I am basically presenting here also on behalf of my colleague Bernd Eschelmüller, who couldn't make it today because right as we speak, there is in fact the final GA meeting, or the final review meeting, in fact, with the project officer happening right now. So you know that the project has come to an end, and it's hopefully a successful one also in the eyes of the project officer, but we're quite confident in that. So to introduce you a little bit, so Alex Thaler has already introduced a little bit the general objectives of this call in general. So, you know, we're going anyway towards cost and energy efficient battery cell production. To introduce you a little bit to the consortium, so I already talked about us, which is AIT. So we were the coordinator in this case. Then together with us was CERT, who's based in Greece, the Sovema group in Italy, CEDATEC in Spain. We got RISE from Sweden, and we got Saueressig, University of Duisburg, and KIT from Germany. So once again, I think it's quite clear why we are working on the topic of going for reduced energy consumption and sustainable and cost-efficient cell production. And just to highlight this more, I think there are several graphs on this, but just to give you an idea of, so let's say, the energy consumption share for the battery manufacturing process, the three main contributors are the formation process, the coating and drying, and the dry room in itself that it usually takes. So those were also the three areas that we loosely tried to focus on the most for this particular project. And the idea was really to go into a project that would benefit the actual battery manufacturer and the OEMs, which is also why we didn't go too much into the materials itself. So there's no large material innovation per se, other than the actual processing of those materials. So in fact, we opted for the most part for an NMC 622 and usually used just some standard graphite, in fact. So the idea was always to try and go for lower production costs and energy demand in all of our experiments. So generally speaking, already introduced sort of like the idea of the sustainable manufacturing. We don't have to go into all of this, but basically it's a combination of the different things, from reducing inactive materials over energy efficient processes, all the way to going for raw material selection and going for longevity of the cells, including the second life part. So we obviously couldn't cover all of this, but we looked at some of the potential energy and cost savings from the production processes that we can see. So you can see some numbers here that are possible according to the literature, basically, that is out there, and compared a couple of conventional production processes, basically from the slurry preparation all the way to the formation and aging and reduction of scrap rate. and looking at some sort of more novel concepts of how to mitigate some of these challenges. So we in this project, or at least the things that I'm showing now, looked at the NMP-based slurry preparation, so basically reducing that for water. Now, and even though we don't have an awful lot of energy reduction here, but I think there's a cost-saving potential here, and of course, we're also looking after the sustainability of this process. Then we went basically for reducing the need for the dry room when it comes to things like slitting or stacking, electrolyte filling, and so on. So everything that usually happens there, trying to reduce the steps required within the dry room, therefore the time it takes for the cell to be in the dry room, or maybe even the size of the dry room. And then looking at the formation and aging itself. So overall, at cell level, if you would achieve all of this, which, spoiler alert, we did not even try within just one project, but there are huge potential cost and energy savings at cell level, at the very least, in these few process steps. So roughly for the project itself, so we had 8 work packages, out of which these 2, so work package 2 and 3, were more digitally driven, and we had 4 which were more on the technical side, so technical in the sense of actually experimental, I should say. And now in the course of these, the next few slides, I would just like to highlight or bring to your attention a few of the highlights from at least some of the most impactful work packages that we had in the project. So first of all, work package 2, so this is sustainability and digitalization. So in fact, what we tried to do here was to go for a improved dry room design, or basically look at what the improved dry room design could actually do for us. So basically, we tried to, in the first scenario, reduce the dry room need just for cell stacking, then drying and electrolyte filling. So it's closer to the conventional process. Now, the final scenario was then to reduce the dry room condition only for the finished stacked cell, basically, and the electrolyte filling in itself. And we could see that essentially for on a theoretical basis, based on a 39 ampere hour cell, which we kind of simulated in this particular process, we were able to show that there is a reduction possible by almost almost 3/4 when we go from, let's say, the state of the art or conventional process to a reduced dry room condition, which is this on the left side. And then in fact, if we actually go over to this process, where we only have the cell drying and filling in one machine, basically, we were able to reduce the actual energy consumption per cell drastically, in fact. And we even came up with a sort of machine design, which could be then the industrial equivalent to this machine. You see, this is almost like a bit of a revolver loading type for the actual filling machine, where you keep a certain number of cells at a specified conditioning sort of step for a certain time before you load it into the filling machine. But that was just a concept stage, but just to highlight, this is actually feasible to be transferred into a real life production. So we also came up in preparation for the battery passport that will be quite important soon. We came up with a data space demonstrator. So we actually set up a data space on our web page, and we try to really come into, or try to comply with, what will be needed for the future of the battery passport sector. Now, I'm not going to go into the details of this model, because that would take up all the time that I have today. However, I definitely invite you to get in touch with us, or the project itself, also on the web page, and check out what we've done there, and maybe we can develop this even in the future a bit more together when data gets available. So very similar actually for work package 3, where we actually looked into model assisted process optimization. So we really looked into the data that we generated for some of the most critical process steps, so the coating, drying, calendaring, the wetting, the drying, and looked at how this correlates to the performance. So what we really tried to do is to cut down on the experimentation side. So you can basically input a couple of parameters that are relevant for the step, and then you could get a little bit of a predictive performance out of this. Now, this is something that is publicly available or will be made publicly available. At the moment, it's hosted on the CDTech webpage. But once again, I invite you to actually get in touch so you can try this for yourself. I think this is a very nice starter, basically, to reduce maybe the trial and error phase with your material. Now, we're not claiming it's perfect, but it's definitely a first step into going into the right direction for sure when it comes to processing parameters. Work package 4, so this is one of the more technical or experimental work packages. Here we tried essentially solvent-reduced electrode manufacturing. So with the traditional water-based electrodes, so we used an MC622, as I said before, so we went water-based right from the start. However, when you do that, we only achieved a solid content of 59% in the slurry. And as you know, this is not particularly high, but as you go to water-based, you tend to have a lower solid content compared to NMP, which is an issue. And by altering the binder system, so going from the more traditional CMC-based to a more lignin-based binder, we actually managed to increase the solid content to 73%. And as you can see here, sort of the orange bits and the blue bits are the performance indicators, or basically the performance of the cells of exactly those lignin-based binders. You can see that we definitely didn't lose any performance. In fact, in some cases, we even gained some of the performance. So we actually certainly managed to get a reasonable replacement here over time. And lignin is basically a byproduct of the paper industry, so definitely a sustainable solution. In work package 5, we then also tried to go for eco-friendly cell designs and validation. So we went with a 3D electrode design. So we did some laser structuring of the cells. And without going into the extreme level of detail, you can see as soon as you go to 1C, 2C, and 3C, you have basically the red as the unstructured baseline and the structured different variations. We actually got certainly better performance at higher C levels. At low C level, so C/2, you could see that we have very comparable and stable performance, so we don't really lose anything, whilst actually keeping the mass loss here at about 6%, so definitely under a critical 10% for the whole cell. And this was done at a 13-layer, 3.15 ampere-hour pouch cell. Furthermore, we actually looked into the formation process, so I'm not going to give you all of the details of the formation process that we studied. However, there is, first of all, a deliverable available from the BATT4EU project, which I'm sure we will make at least parts of this public after the final review meeting, which is happening right now. Plus, there's a publication out there which came out of this project, which we're quite proud of as well. In short, we actually managed to significantly reduce the formation time while not losing any of the performance, which we then transferred also to work package 6, where we simulated the industrial implementation of all the technology that we had here. And as a last part, that I want to introduce you to, we looked at the different drying concepts at component level and stack level. So here at component level, meaning the electrodes themselves, we actually dried them under ambient conditions, under, well, just as a baseline, of course, then under dry room conditions, which is sort of like the yellow boxes that you see all over here. And the sort of reddish boxes here give you the vacuum oven drying at only a few minutes, like 30 minutes or 60 minutes. And you have the corresponding ppm basically of water that we measured on the KF titrator. As you can see, basically with the vacuum oven, we actually achieved, maybe not so surprisingly, but we actually achieved much lower water content compared to dry room storage, even for up to 3 hours. Now, when we go to the stack level, which is probably more important, so we actually did the pouch stack for at least 1 amp/hour here with these measurements. We also managed to get down in 30 minutes and 60 minutes vacuum drying at 80 degrees to a very good moisture level, or to an acceptable moisture level, which translated into a good performance, or at least no measurably fewer or inferior performance compared to, let's say, properly or conventionally dried electrode and cell components. So with that, I managed to actually go to the last slide now here. So essentially, these drying concepts also went into a dry room reduction report. So basically, we tried to get this into a simulated production environment as such, by showing that the drying conditions that we applied here were actually able to achieve the similar or same performance levels as we would manage with conventionally dried electrodes and cell components, which then led into the concept that I introduced initially, where we could actually assemble the entire cell all the way up to the electrolyte filling, and you would then give this finished or semi-finished and dry cell into the machine, where you would do the final drying step, essentially in this sort of revolver concept here, and then feed that into the filling chamber of an electrolyte filling machine, where you would do the final stack. Now, the project itself didn't develop the machine, but together with Sovema, who is a machine manufacturer, we developed the concept for it and got the confirmation that this is definitely a feasible concept to work on in industrial level. Right, and I think with that, I'm hopefully on time. I think we managed fairly well, and I thank you for your attention. And obviously, I'm happy to take some questions from your side right now, or I'm of course also here to answer the questions in chat.
Great, thank you so much for that presentation. Great to see what Batwoman has achieved in the past years. There was one question in the Q&A from Yasmin, asking whether there is a plan to prove the cyclability of the aqueous process cells over more cycles, like 1500 plus.
Well, yes and no. So no, in the sense of the final project deliverable, because we ran out of time. However, there is a yes, because the cells are still running. So we're actually looking at that at the moment to see how far we can take them before they actually lose significantly in capacity. And certainly beyond the project, I think we will keep on working on the concepts that were developed here and try to push it even further, because we obviously worked quite holistically. So there were quite a lot of different approaches to try and work on, which I think is great, because then you see the full picture. But at the same time, of course, you can't go into just one of the aspects in like a 3-year project kind of detail, right? So we will continue to work on that and look into that. But I would say that this was actually a great example of not trying to have the best ever performance possible that a battery cell has ever seen. However, it was trying to be at the industry standards while reducing some of the conventional energy demanding steps. So that was a nice project really to work on.
Great, and maybe one last question which has popped up, asking which cell system you use for Batwoman from a chemistry point of view.
Oh yeah, okay. So I only mentioned it basically briefly, or it was on one of the slides, so you can't see it. But what we used was a conventional NMC 622. The reason why we went for the 622 was because, first of all, I think there is, when you go for a more, let's say, cost balanced material selection anyway, there has been a discussion, and I think there is still a discussion as to how beneficial NMC 811 or even higher nickel content actually is for some of the cells, if it's really necessary. So we went with the 622. Plus, at the time, especially when we were writing the project, it was quite impossible to achieve several hundreds or thousands of cycles with NMC 811 that has been processed by water based processing. However, I do know, since we're also part of the NOVOC project, that was a focus more of that project as well, and some others. So we went with the 6-2, so we could focus entirely on the production process and not so much onto optimizing the material itself. And on the anode side, that was a graphite for the most part. We also experimented with a bit of silicon-based graphite, but graphite was the most important anode component. And you can see the binder studies basically also in one of the slides. So it was CMC SBR as a baseline for aqueous processing, and we then replaced the CMC more and more with a lignin-based binder system.
Thank you so much. Thank you again for your presentation and answering questions. I will now move on to the next speaker directly, which is Sina Starborg, who is the coordinator of the NOVOC project. I leave the floor to you now for the last presentation of today.
Thank you. Thank you so much for inviting me.
Thank you for coming.
Yeah. So hello, as Timothy said, my name is Stina Starborg, and I'm coordinator for the NOVOC project, and I'm working at RISE, Research Institutes of Sweden. And in this talk, I will present how we are working to eliminate volatile organic compounds from lithium-ion battery manufacturing by developing both water-based processes and dry electrode processes. Yeah, so our main objective with this project is to implement environmental friendly and non-toxic manufacturing routes for lithium-ion battery cells, covering both anodes and cathodes. And at the same time, we will have a very clear industrial ambition. We target competitive low-cost cells in both cylindrical and pouch formats, suitable for the fast-growing electromobility market. In short, we want to demonstrate that you don't have to choose between sustainability and performance or cost. And as a background information, the project duration is 48 months. It started 1st of September 2022, and it will continue until August next year. And as I said, RISE is coordinating, and we have 15 partners from all over Europe. So you have several partners. So you have Technische Universität from Braunschweig, from Germany, Uppsala University from Sweden, Nanopow, providing materials from Norway, Talga from Sweden, Kansai Altan from Turkey, providing binders, and Centro Ricerche Fiat from Italy, working on the digitalization and specifications. And we had Graphmatech, but they are not longer part of the consortia. And then we have Sidetech from Spain, working on the anode formulations for wet processing, and Latvia University working on the processing. Avesta Battery Energy Engineering from Belgium, working on the upscaling on the wet process. And then AIT from Austria, and CEA from France, And also we had custom cells, but they went insolvent, so we had replaced their work for other partners. And then we have BATT micro battery working on the cell level, and UTMA research from Austria that is working on the dissemination and communication. And then we have SNAM working on the recycling part, and RISE is working also on the LCA part. So if you go to the NOVOC concept, is to combine process innovation with digital tools and life cycle thinking. And we have several partners contributing with materials for the cathode and anode and binder. And like Talga, Nanopau, RISE have worked with this. Then we have Kansai Altan and others. And then we have Uppsala University that was working on the formulation and lab scale work on electrodes together with other partners. And we have then formulated recipes and methods for AKE's electrode manufacturing and dry electrode manufacturing. And then we have cell assembly at BARTA and ABI or AIT. And then we will do testing at CDTech and BARTA. Yeah. So this is the workflow, the concept. And if we go to the NOVOC project, how it's worked. So we had a work package working on the cell requirements and specifications led by CEA as an input. And then we working on the active materials, which is NMC 811 and silicon carbon graphite materials on the anode side, and binders from Kansai Altan among others. And then we worked in the optimization at lab scale with AKE's processing of anode and cathode, and RISE processing anode and cathode, and also identified the cell harmonization or cell designs to be used. And then we have made electrodes at pilot scale and make upscaling. In the project, we are now in the phase where they are working hard on the upscaling phase. So we have not assembled the demonstrator cells yet, but smaller cell variants. So the testing will be performed during spring. And during this phase, we are also working on modeling and digitalization and the recycling process of these kind of materials, since you need to focus on the recycling also because it's new electrode processing. So if we go into the AKE's wet cathode manufacturing process, the Austrian Institute of Technology, AIT, led the pre-development based on NMC 811, which is a nickel-rich lithium-ion cathode. And they have demonstrated water-based slurries that remain stable in pH over time, and they have manufactured multi-layer pouch cells of around 1 ampere hour with specific capacity and cycling performance comparable to NMP-based processes. And these formulations and coating methods are now transferred into upscaling. And we have also made a surface coating of NMC 811 at RISE in order to make it more stable for wet processing. And this material have been upscaled and will be made larger scale electrodes also. And ABI and AIT are working on the upscaling, where they have some challenges with bubbles forming, especially when they use the slot die coating, and they are working on solving this. And meanwhile, they will do pilot scale cathodes at AIT and using the comma bar coating instead. And if we go to aqueous wet process, then the work was led by CDTech with anode material provided by Talga. And the team developed a new mixing protocol for about 5% silicon in a graphite-based slurry, achieving a very stable rheology and uniform coatings, which was made by comma bar coating, but will be at ABI. They have upscaled with the slot die, and it works fine. And these half cell tests from CDTech shows that it is good, very competitive results from an aqueous process. And now that is handed over to ABI that are still working on trials, but it's looks good. Yeah. And then we have the dry manufacturing process, which is led by TUBS, or Technische Universität Braunschweig. And here they have eliminated liquid solvents entirely and work with powder granules and polymer binders, typically PTFE, and they use graphite anodes with 97.5% active materials and some conductive carbons and PTFE, and also NMC 811 cathodes. And both dry anodes and cathodes show high initial capacities and a stable cycle. And now this is transferred to upscaling, where they have some challenges also. But they are also working on this at the moment, and they are confident that they will solve it. So one of the key issues are inhomogeneous dosing of the dry granules, which can lead to ribbing effects in the calendar gap and non-uniform electrode thicknesses. They also observe curling of freestanding electrodes and some adhesion problems. And they also need this power dosing system, which is essential. But these learnings are very valuable for future industrial dry electrode lines, which highlight which equipment and processes are controls that are critical. So it's a very steep learning curve. To summarize, we are now in the between stage 2 and stage 3 in the project, so we are not having any results to show for the final cells made by these. So the cells will be produced this autumn and early next year, and then we will do the testing. And recycling work is ongoing, where we use electrode materials, meanwhile they wait on the cells. So, but if you are interested to know more, please contact me and ask me some questions. And I'm happy to come back to you if needed. And thank you so much for attention. And please let me know if you have any questions.
Thank you so much, Tina. Thank you so much for presenting those results from Novak. There were, I see 2 questions. The first one asks how the data collection happens within the project, I imagine.
Yeah, it happens at both the slurry processing and also electrode processing. There we collect data for rheology measurements and such things. So it's connected, and then it's supposed to connect to the cell quality in the end.
Okay. And what would be the advantage of going for water-based with NMC 811 or NMC 90?
Can you repeat the question?
Yes, so they ask, what is the advantage in going for water-based NMC 811 or NMC 90, or just removing volatile components and other significant advantage for going water-based?
Yeah, I think it's more challenging the more nickel you have. So we would like to see more our approach with the where we coated the NMC material with the LF iron phosphate. I think that's an interesting solution, and maybe then you can go to higher nickel contents.
Great. Thank you so much. I will move maybe to a last question from my side, but for all 3 speakers of today, if Marcus and Alex are also still here, but I will ask it first to you, Tina, maybe. If you could please, in 1 sentence, summarize what you identify as the main success of this project and how we will contribute to a European battery value chain. And that will be the same question for Alex and Marcus.
From my perspective, I think we have very good competence in the my consortium. I'm very proud of the members. They are very collaborative, and if we have challenges, we can solve this together. So it's a matter of cooperation.
Thank you very much. Last statement from Alex, maybe, on the success of your project and what's coming.
Yeah, I think compared to the Chinese competitors, which are simply huge, that was what I was mentioning within the slides, in Europe, we need to take care or even work with interfaces between different partners, because we will probably never get that big. So we need to put very much emphasis on working together and being fast. If that even allows us to compete with the Chinese competitors, I have no idea, or actually I doubt it, but there is no way of not trying it. Yeah, so that's my point where I am.
I see. Thank you very much. And Marcus?
Yeah, I think what was nice about this project, I think I mentioned even during the talk, was that it wasn't about breaking record numbers in terms of energy density and these kind of things, but actually looking into some realistic industrial innovation. So I think probably out of all 3 projects, I think there would be something that we could now take over by 1 or 2 manufacturers basically, and maybe develop further and actually, you know, make some significant savings in the production process. I think now the challenge, I think the projects have delivered, I would say, for what they could. And we are particularly proud of the BATT4EU project and the partners. I think now the next challenge would certainly be to try and get some of this stuff really into industry and then try to really develop a significant advantage for the European battery value chain.
Great, I totally agree. And thank you so much, Marcus. Thank you so much to the 3 of you for coming to speak about your projects today. Thank you to the audience as well for coming to listen to their results and achievements within those. And from there, I will simply leave it at that. Thank you again, and we'll see you on the next edition, which is not planned yet, no set date, but we will keep you informed through email, social media, and others about when it comes. Thank you again, and have a great rest of the day.
Thank you everyone.
Thank you.